All right, hi everybody. So I just want to quickly go over this AP Physics 2 kind of practice exam Google form. The format's a little bit different because I want to kind of mimic the format that's on the AP test. Just really quick, if you haven't seen the video that I posted, if you're planning on taking the AP test and you haven't seen that video that I posted kind of about the AP test and what to expect and what the format looks like, I posted that in Classroom, so give that a watch. I didn't post it as like an assignment, I just posted it in the stream. Oops, that's not what I wanted to do. But yeah, so give that a watch. If you have any questions, let me know. Quick little side note, I'm going to post this on Tuesday. Tuesday. So I'm also planning on just being, I guess, passively in Zoom all day. So I'll just kind of be here working my stuff, and then if you have any questions, just let me know. I want to be able to answer questions for you for the AP test. So yeah, we're going to go over this questions, and again, the format's a little bit weird, but here's the link to it. Hopefully this should link you to this PDF. I crossed out a few of these questions because we literally just did them. So we did them when we were looking at electric potential. College Board kind of pushed out this exam. They took old exam stuff and they reformatted it to match the format that we may expect to see on the AP test. So I was like, okay, final thing, let's just kind of look at what they're posting as practice for this test and kind of what format we can expect. So yeah, we're going to be looking at that. So then you'll just upload it like a PDF or a .docx like you will on the actual AP test. So yeah, I just kind of went ahead and typed out the answers that I wrote. Not saying these are like great answers. I think they're okay. Some of them are a little bit like too mathy, I'd say. But yeah, so I just kind of wrote out what I did, and I just want to walk through them. So with this question, A, B, C, D, E, we did it already. So we did it on May 6th. If you want to go back, you can look at the assignment from May 6th. I think it was just electric potential and field. And I went over those, so I won't go through them again. But yeah, then what we're saying is, okay, we have these two spheres. Just a little reminder about the spheres. We said, okay, we have X and Y. And we said in that situation that Y has a greater charge than X. If we have these lines of equipotential, we kind of reach like a more maximum equipotential for X, like closer to it. And Y, our maximum equipotential, it's not even like close to where Y is. So we still have some more to go. We just stopped drawing in the field lines. So I think this one stopped at like 100 volts or something, and we're pretty close to X. But here we stop at 100 volts, and we're nowhere near Y. We still have 120, 130, 140, 160. We just kind of stopped drawing in the equipotentials. So Y has a greater charge than X, and that's what we need to know for these questions. And they're both positive. So in this case, we're drawing the electric field throughout distance, where we're saying, okay, let's put X at 0, and let's put Y at 15 centimeters. And we drew out the electric field, and it's a pretty good graph. It shows this R-squared relationship. I kind of came into Desmos, and I said, okay, well, let's look at how these compare to each other. You don't need to do this. I spent time doing this. I'm kind of Desmos flexing on you a little bit, being like, yeah, look at what I did with Desmos. But it doesn't really matter. But so yeah, we see this R-squared relationship where when we go away from a charge, our field will decrease. And then over here, we see this kind of decrease in field. Not so much decrease, but a more negative field. So it asks us, what's good about this, what's bad about this? So for F, one aspect about the graph that correctly, this is my answer, that correctly represents the electric field is that the electric field is positive closer to sphere X and negative closer to sphere Y. The electric field indicates what magnitude and force a positive test charge would be forced with if it were brought near to this charge configuration. Early in the question, we'd established that both sphere X and Y are positive. If a positive charge were brought near to sphere X, it would feel a positive force to the right. So it would be pushed to the right because of this repulsion. If a positive charge were brought near to sphere X, it would feel a positive force to the right. If a positive charge were brought near to sphere Y, it would feel a negative force to the left. Also, the graph correctly shows the 1 over r squared dependence of electric field. As the distance gets closer to the source charges, the electric field rightfully goes to infinity, as 1 over 0 is just infinity. So yeah, just kind of the direction is good, that it goes to negative. That seems weird, but it's saying, hey, if we brought a positive charge next to this positive charge, it would be pushed to the left. It would be pushed in what we call the negative direction. And they both show this curve, this 1 over r squared, that of course we get, even if we look at a Desmos graph, we see this nice 1 over r squared relationship. And here's my combined one. I don't know if you can use Desmos. That's a good question. That's like my question. But yeah, so then the graph incorrectly shows the location of 0 electric field. So they show a 0 kind of around 10-ish. So earlier we established that sphere X has a weaker charge than sphere Y. From 0 to 15, the electric field from X is acting to the right. From 0 to 15, the electric field from Y is acting to the left. There will be a zero electric field when the two fields are at the same magnitude, but in an opposite direction. The graph shows that the zero of electric field is closer to sphere Y, but this is incorrect because Y creates a stronger field. It will be harder to cancel out. It will cancel out more so between 0 and 7.5 centimeters on the graph, so more to the left half of the graph. Yeah, so it's stronger. So it probably won't be 0 closer here because, again, we have this r squared fall off, so it'll be even stronger, and we have a stronger charge. So Q is bigger, R is lower, which means we have a stronger field closer to Y because it has a bigger charge. So we'll more than likely see 0 that is closer to sphere X because it has a stronger, or has a weaker charge, so it'll be easier to cancel that out. So yeah, that's kind of all there is for that question. And then on the actual AP test, you'll have two different documents, one for question 1, one for question 2. So here's my other document for question 2. This one's a little bit, I kind of wrote more because it's a paragraph length response question. This looks like one that we've done, but they've switched up the questions, and I like the new questions. I think they're smart questions. So here we're saying, two students observe water flowing from left to right through the section of pipe shown above, which decreases in diameter and increases in elevation. The pipe ends on the right where the water exits vertically into the bottom of a large, deep pool. So for the first one, we're saying a bubble of air passes point A and later point B without changing temperature. In a clear, coherent paragraph length response that may reference equations, state whether the volume of the bubble at point B is greater than, less than, or equal to the volume of the bubble at point A. So is the volume bigger at A or bigger at B? So let's see what we got. This is just what I wrote out. Again, not saying it's perfect, not saying it's great, but it kind of follows the format and something that we may want to think about. Yeah. So at point B, the volume of the bubble is less than the volume of the bubble at point A. No, wait, hold on one sec. All right, so I had stuff fine, and then I wrote the wrong thing for that one. But so at point B, the volume of the bubble is greater than the volume of the bubble at point A. And so kind of arguing why. At point A, the bubble is under a high pressure. At point A, there is a large amount of pressure because of the weight of the column of water above it. Pressure is defined as force per area. Because there is a larger number of water particles above point A, there's a large gravitational force which applies a pressure at point A. So there's a larger pressure at A. This is also dictated by the equation P equals P naught plus rho GH, where H refers to depth. As the depth increases, so does pressure. At point B, the pressure is lower. There are less water particles above the bubble at B, which provides a lower weight force, which supplies a lower pressure. Again, by the equation P pressure equals P naught plus rho GH, as the depth decreases, the pressure decreases. Because the pressure is lower at B, this means the volume will be greater at B. So we've already established this idea. Pressure is going to be lower at B than at A. So that's kind of one of our main arguing points. So yeah, so then pressure, and then we're saying because the pressure is lower at B, this means the volume will be greater at B. This is shown by the ideal gas law, PV equals nRT. The number of moles, N, the gas constant R, and the temperature T are constant. This means that the volume is inversely related to only the pressure. As the pressure decreases, the volume will then increase. Physically, this can be explained at a particle level. The air particles inside of the bubble create a pressure by colliding with the surface of the bubble. When at the point A, the net force from the collisions are lower because of the collisions with the walls of the bubble from the water. So we have the pressure from the bubbles, from the water particles are colliding, and we have the air particles are colliding outwards. So the net kind of pressure, the net force, is going to be lower because we have more inwards forces. At point B, the net force provided to the area of the bubble is larger in the outwards direction because there are less water particles acting against the outwards push of the air particles, which means our volume will be bigger. All right, so hopefully that made sense. Suppose the pipe remained a constant diameter, but the elevation of the pipe changed the same amount as in part A. Would the difference in pressure between points A and B be greater than, less than, or equal to the difference in pressure between points A and B when the pipe narrowed as in part A? Justify your answer. So here I justified my answer. It may be too mathematical for what they're looking for, but they didn't supply a key, so I really don't know what they're expecting on this AP test. So my answer is if the pipes were at a constant diameter, the difference in pressure between A and B would be greater than the difference in pressure between points A and B when the pipe narrowed. This is dictated by the continuity equation and Bernoulli's law. In part A, B was narrower than A, which means the area of B is less than the area of A. By the continuity equation, in order to preserve the conservation of mass, the velocity at B must have been greater than at point A, and that's the equation AV equals AB, AV equals AV. So the area at A times the velocity at A equals the area at B times the velocity at B. Bernoulli's equation, PA plus rho G HA plus 1/2 rho VA squared equals PB plus rho G HB plus 1/2 rho VB squared, is a statement of conservation of energy. When B is narrower than A, the kinetic energy term at part B is greater than that at A. In order to maintain conservation, the pressure term at B has to be lower than in the new situation. This is because in the new situation, with the constant diameter, the fluid at B has less kinetic energy because it's moving slower. The additional energy must go somewhere. It goes into the pressure term because the potential energy term is simply a function of the position. So yeah, that was a lot of words, and hopefully it made some sense. Now we have this situation where we're saying, okay, let's put a prism in water and lift it. The triangular prism is fully submerged in a tank of water while suspended from a rope without touching the bottom of the tank as shown in figure 1. At time t equals 0, the rope pulls the prism upwards at a constant speed. At time t1, the top of the prism reaches the surface of the water, and at time t2, the prism has been completely removed from the water, shown in figure 2. The prism always moves with constant speed. The graph below shows the tension in the rope as a function of time. In terms of relevant physics principles, explain the behavior of the tension versus time graph from t equals 0 until a time after t2. So this one, again, I kind of went lengthy with it, but I'm pretty happy with this answer. So the forces that act on the prism in this situation is the upwards tension force, the upwards buoyant force, and the downwards gravitational force. The gravitational force is always constant because the mass isn't changing. The buoyant force is a function of the volume of the prism that is submerged. The tension force then changes accordingly because the prism is always moving at a constant velocity. This means that the net force is equal to 0 because the acceleration is 0 by Newton's second law. We have the relationship that Ft plus Fb equals Fg. The buoyant force is equal to rho Vp g, where Vp is the volume of the prism that is submerged in the water. As this Vp decreases, so does the buoyant force. This means that force of tension must increase accordingly as shown in the graph. So that was just setting up all the things that are acting on this. How is tension? We're going to reference volume and tension. So just referencing how is volume, when we're talking about volume, why does that matter in terms of tension? So we can just come in here and say from 0 to T1, the prism is completely submerged. Vp isn't changing, so the buoyant force doesn't change. Therefore, the tension doesn't change either. From T1 to T2, the volume of the prism is decreasing. This means that the force of tension is increasing. This is happening at a non-constant rate because the prism's volume doesn't change linearly as it is pulled out of the water. At T1, the tip of the prism is pulled from the water, causing a low decrease in Vp, a small increase in force of tension. As time goes on, the rate of volume decrease is increasing, so the tension increases because we kind of get thicker towards the base. From T2 onwards, Vp is 0 because the prism is no longer submerged. The tension is equal to the weight force. So yeah, we described each part of those. And yeah, so that's kind of it. I think this is a good conceptual question. Hopefully we see nice questions like this on the actual AP test. Again, I don't know what's going to go on with that. But yeah, so that's kind of it. This is the last thing I'll teach you. It's kind of a bummer. I'm sad. Okay. Yeah, so hopefully I'll see you guys on Zoom. I'll post a link and say, hey, I'll be in Zoom for most of the day. And hopefully see you there.